Welcome to Chapter 8, Sections D and E. Today we're talking about permutations and combinations. I'm choosing to do these two sections together because to the beginning student, it's not going to be immediately obvious from a lot of the word problems that we'll see whether the problem is about a permutation or a combination. So I think it's important to look at them together so that we can really compare and contrast them appropriately. All right, let's look at some formulas before we do any problems. So this first formula is actually not in your textbook. This is the formula for calculating how many permutations we would have for a group of objects. We are, in this case, there are n total objects, of which we are picking r of them, and we're going to arrange them in a specific order. That's really what makes a permutation different from a combination. A combination does not care about order. This is kind of confusing because you've probably heard of a combination lock, and the common English parlance does not agree with the mathematical definition of what a combination is. So I like to call those permutation locks. Anyhow, the formula at the bottom, we actually saw that in the last video. I think we saw both of these in the last video, actually. But this is definitely in the textbook. It's also in the formula book. That's the formula for a combination. You'll notice that they're really similar to each other. What's the difference? The difference is that the combination one is being divided by this extra r factorial, and that's not just a coincidence. I want you to think about this for a moment. If we have n objects and we're going to choose, so we're doing a combination here, choose r of them, there are exactly this many different groupings that we could make. Now that's without regard to any order. So if I had 4 objects and I was choosing 3 of them, maybe my 4 objects are A, B, C, and D, a grouping of A, B, C is exactly the same as the grouping of C, B, A, because it's the same 3 objects. So we would not count that more than once. If we were to count how many different orders there are, we would take each of these different combinations and then multiply by how many different orderings they have. How many different orderings do they have? They have exactly r factorial orderings. So multiplying the combination formula by r factorial, the r factorials cancel, and then we get this up here. If that was too much for you for right now, maybe come revisit this part of the video later on and it'll make more sense. Apologies. So first, let's just kind of look at the difference of these two. So here's the 4 symbols I referred to a moment ago, A, B, C, and D. So how many permutations and how many combinations of each of these can we make? I'll do the combinations first. So I'm going to take 3 of these 4 symbols. So I might choose A, B, and C. I might choose A, B, and D. I might choose A, C, and D. Or I might choose B, C, and D. Those are the only combinations that I can pick, that I can choose, I should say. Since I'm choosing 3 out of the 4, in each of these cases, I'm leaving out one of the letters. So I left out the D, I left out the C, I left out the B, and then I left out the A. There's only 4 combinations. How many different permutations are there? Well, I still have ABC, but I'm also going to have ACB. I'm also going to have BAC, and I'm also going to have BCA. I'm also going to have CAB and CBA. That's just the permutations of this first one. So each of these 4 combinations is going to give me 6 different permutations. So in total, we're going to have 24 permutations. I'm not going to write them all down, but I think you can imagine what they are, whereas we're going to have 4 combinations. And so this, to repeat what I said on the last video, how many combinations are there? Well, in this case, there's 4 factorial divided by 3 factorial times 4 minus 3, which is 1 factorial. Calculate that in your head, right? This is going to be 24 divided by 6 times 1, which is equal to 4. If I were to take this expression and then multiply by my r factorial, which in this case is 3 factorial, So that cancels. That expression would only be 4 factorial, which is exactly equal to 24, which is how many permutations I had. Before we go any further, I think I should probably tell you how to do this on the calculator quickly. Yes, you can use the formulas with the factorials. We talked about that in the last video. We're going to menu and then probability. You can just use that. Or you notice when you're on the screen, hey, we've got permutations and combinations right here. They both work in the exact same way. If I choose permutations, if I wanted to do, as in the last one, 4, pick 3, I'll just do 4, comma, and the comma button is right down here, 3. There you go, that's 24. If I want to do a combination, same thing, 4, comma, 3, there's your 4. Okay, looking at a slightly more complicated example, because it's pretty rare we're going to only have 4 objects to be dealing with. We have 5 letters here. Okay, A, B, C, D, and E, blocks placed in a row. How many different permutations could we have? So this is very nice. The problem is using the word permutations, so we don't even have to think about which formula to use. We could use the formula that we saw earlier. So there are 5 objects, and we're going to divide by, it was n minus r factorial. In this case, n and r are both 5 because I'm picking all 5 of the objects. So that's divided by 0 factorial, which is equal to 1. So it's just 120. As a shortcut here, whenever we're arranging all of the objects in a row, it's always just going to be n factorial. So anytime that I know I'm arranging 5 things and I'm doing all 5 of them, it's 5 factorial. And I'll immediately jump to that. And we can see down below that the book thought of it in the same way. And I want to just point out one other thing, because I'll use this trick in future problems, I'm sure. A visual aid that I'll often use is I'll just draw out the blanks that I have, and then I'll ask myself, how many different blocks can go in the first blank? Well, there's 5 there. How many can go in the second one? 4. In the third, 3. In the fourth, 2. And in the last one, there's only 1 left. Multiply those together, and we get 120. Moving down to letter B, we can kind of use that same technique there because we still have 5 blanks. But we know that the last block has to be a C. So how many options do we have for the first one? There's 4 that could go there, 3 that could go there, 2, and 1. So my answer for the second problem here should be 4 factorial or 24. For letter C, we can approach this in the same way. In this case, we know that A and B have to be in those particular places. So how many options do we have in the first spot? There's only 3 letters that can go there, only 2 that can go there, and there'll be 1 left over. So for letter C, we should have 3 factorial, so that'll be 6. And for letter D, we know that the 5 letters have to begin and end with a vowel, but we don't know what order those vowels need to be in, so we need to consider both A in the beginning as well as E in the beginning. Both scenarios are going to have 3 blanks left over, so they're each going to have 3 factorial or 6 different permutations associated with them. So the grand total here should be 6 plus 6, which is 12. There's other ways we can complicate things. So in this problem, we have 2 of the books which have to be found together. It does not specify what order those 2 books need to be in when they're together, so we need to consider any ordering of them, and they could be at any position on the shelf. There's 2 ways that the book offers to do this. I'm not a fan of the first one, so I'm just going to show it to you. So A and B could be in the first 2 spots, or the second 2 spots, or the third 2, fourth 2, or the fifth 2, the last 2 spots. And then in each of those, we have 2 different orderings that we see before us. So there are 10 total orderings listed here. For each of those, we don't know, however, what's happening with the remaining 4 spots. And it doesn't matter whether those 4 spots are consecutive or broken up. The fact of the matter is, the very first of those blanks has 4 options, the next has 3, the next has 2, and the last one only has 1. So for each of these 10 scenarios, we have 4 factorial, or 24 different arrangements of the other 4 books. So that's a grand total of 240. Now that works out just fine. The way that I like to do this, I'll actually use this picture to help, is I kind of imagine the A and B as being a single unit, because we know they have to be together. And knowing that, I imagine this not as being 6 different books in a shelf, but I just imagine it being 5 different books in a shelf. Right? So we've got 1, 2, 3, 4, 5. And so I'll say, all right, how many different ways can those 5 books be arranged? That's going to be 5 factorial, or 120. But then I know that I have that block of 2 with the A and the B, so I'll say, how many different orderings can those 2 have in their own little pairing? And they can be arranged 2 different ways. So I'll multiply 120 by 2, and I'll still get 240. And that's exactly what method 2 is. They talk about tying a string around the books to keep them together, but that, I don't know, that's the way that I like to think of it. But if you want to list out everything as they did in method 1, you can, but you certainly don't need to draw this huge grid. All right, next problem. How many different teams of 4 can be selected from a total squad of 7? No restrictions. Letter A, let's do that. Perhaps your first thought here is to make 4 blanks, because you have 4 people that you can put on the team. And you're thinking, well, there's 7 people who could be chosen first, and there's 6 people who could be chosen second, and there's 5 who could be chosen third, and then there's 4 who could be chosen last. And you would do 7 times 6 times 5 times 4. You get an awfully large number, and you'd be completely wrong, because that would give you how many different orderings we could have of this team of 4. Like if the team had to have a captain, a vice captain, I don't know, treasurer and a secretary. Couldn't think of anything else for that metaphor. There we would have 7 times 6 times 5 times 4. But we're just talking about a team. We just want 4 equal people. So the order here actually doesn't matter. So that's not the way we want to do it. We just want to use our combination formula, 7 choose 4, and we get 35. So this is where the challenge comes in with these problems. I didn't even tell you that I swapped into section E already, but I did. We're now talking about combinations. The difficulty on the exam will be figuring out, is it a combination or is it a permutation? All right, letter B. The teams must include the captain. So I guess out of these 7 people, so there's 1 captain and there's 6 not captains. Out of that 1 captain, I need to choose the 1 captain. And out of the 6 non-captains, I need to choose 3 of them. So what's that going to look like? It's going to be 1 choose 1 times 6 choose 3. That'll give you a grand total of 20. All right, here's a slightly more complicated one. We're going to choose a committee of 4 people out of 7 men and 6 women. If there's no restrictions, how many different committees can we choose? Well, how many people do we have in total? There's going to be 13. We're going to choose 4 of them. So it's 13 choose 4. Grab a calculator, probably that's equal to 715. No problem. Letter B. We're going to choose 2 out of each of these binary sex options. So we know that out of the 7 men, we need to choose 2, and out of the 6 women, we need to choose 2. So we're just going to multiply those 2 together. Again, grabbing our calculator to compute that. And letter C, there needs to be at least 1 of each sex. So 2 ways to do this. First, we could consider the scenario in which there are 3 men and 1 woman, and then add to that the scenario in which there are 2 men and 2 women, and then add to that the scenario in which there's 1 man and 3 women. So to do that, we're just going to take a whole bunch of combinations, multiply them together where appropriate, and add together where appropriate. There is a typo here, by the way. This should be a times. Thank you very much, textbook. So this is 3 men and 1 woman plus 2 and 2 plus 1 man and 3 women. Add those 3 together, we get 665. Awesome. Or you might consider, okay, I can work out the total number. We already did the total number, right? 13 choose 4 up in letter A. And I'm going to remove from that the situations in which there is not at least one of each. So the situation in which there's all men, and then also subtract the situation in which there's all women. And that'll get you the same answer. I don't know. That one is probably the one that would spring to my mind first. I'm usually looking to take these shortcuts by using the complementary events, but whatever. Now I want to do one more because I hate this problem. This problem was on the 2017 Time Zone 2 Paper 2 exam. And I definitely did not do this one right when I tried to take that test. The answer is just so large. It was so hard for me to imagine what was going on here, and my mind blanked. But it's not too bad. We just follow the principles that we've set forward already. So take a moment and read it, and get ready to jump in. So the way that I like to think about this one is, first, let's consider the other non-science papers. How many different orderings do we have for those? Well, there are 15 of those papers, so there are going to be 15 factorial ways that those can be ordered. So later on, I'm going to have to multiply something by 15 factorial. We'll come back to that. At the same time, I want to imagine those 15 exams spaced out. And now I want to place my first science exam someplace in here and say, like, how many different options do I have for my first science exam? Well, it could go in one of 16 places. Here they are: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So it could go in between any two of those exams or on one of the ends. So the first science exam has 16 different options for it. The second science exam has each of those 16 places to choose from, except it could not be in the same place as the first one. So that means that the second one has only 15 options. And then the third one has each of the previous options, but except for the places where the first two went. So it is going to have 14. So for a final answer here, I need to multiply 15 factorial by 16 by 15 by 14. And that's a gigantic answer, but it's the right one. And there it is. From reading the mark scheme, it seems as though they were allowing students to just write this, but I would not take my chances with that. I would prefer that you write it out as this. Again, you can just write it as 439 and then a whole bunch of zeros, because rounding to 3 significant figures. You could do a scientific notation, 4.39 times 10 to the whatever. I don't feel like counting those decimal points, but that was how to do that one. And so you can see, I mean, this number is like crazy big. And that's part of the challenge to permutations and combinations, is that you won't always be able to list out all the different ones. You've got to really trust yourself that you've used the formulas correctly and thought about the problem appropriately. You have to think about whether order matters or not. They're a bit of a challenge at first, for sure, but we're going to practice a lot in class. We're going to have plenty of opportunity to work on ones with various language tricks and so forth. Anyway, that's the basic deal with permutations and combinations. As always, there's still some other tricks that can be thrown at you. Hopefully, you find them all to be equally trick as treat. That was a dumb line. I'm going to end this video there.